Okay, again, I hope everyone can see that. I don't have the preview, but again, it doesn't matter. Okay, good. Very quickly going through this material now. Okay, so all this was presented already. I spoke quite a bit about, soft robotics, an area of research I'm very interested in, and how we have used that for, surgery, soft robotics for surgery. Before I went there, I gave an overview of laparoscopy. And yeah, please do have a look at the slides and the video that I have given. I mentioned a number of procedures, and now with the guest lectures that you have seen, even more important information on that, and also how robotics can be used in this context. Yeah, so I won't go to those now again. We have done that beforehand, but the recordings are there, so you can look at that. Then I also introduced now the industrial efforts there to create new robotic devices that can be used to carry out minimally invasive surgery. Again, that was also very much underpinned and supported this kind of area by the different guest lecturers. For example, Alberto Arezzo spoke quite a bit about different systems in use, how they are welcomed by surgeons and where the issues are. And then speaker last week perhaps spoke about from the perspective of a urologist, surgeon in urology, and how great the Da Vinci robot is, and where possibly issues are, but also new developments. And Alberto Arezzo looking at it from a position of a colorectal surgeon, maybe being slightly more critical with respect to the Da Vinci robot. So yeah, please do have a look at that. And there are also some, aspects summarized in those lecture notes. Please have a look at those relevant for the exam. Yeah, so overview of these different techniques and systems that are being developed. Again, I'll just skip through those because we have already talked about them. Yeah, multi-port surgery, single-port surgery. You should know about that as well. Yeah, and examples, which you please have another look at. Yeah, again, summaries along the way for you to, focus your mind on what are the important points with respect to the exam. But obviously, you are also invited to go beyond that, look at the relevant literature, to inform yourself. So that was on the industrial side, so really systems that are already in the market, or there is the intention to bring them to market very quickly. But there is lots of research happening, some of it possibly more blue sky, but really, again, trying to come up with new solutions to overcome the disadvantages of laparoscopic surgery and the more standard robotic assisted minimally invasive surgery. So these are the research efforts. And again, please have a look at the slides and the videos that are available. So number of systems being developed, and we have these snake-like robots, continuum robots, and we have a special kind of continuum robot there. We have the concentric tube robots, also very interesting. They allow for quite some miniaturization. And here more examples on that. Some other approaches in the continuum robot field. And I also shortly mentioned more kind of amateur-like approaches to contribute to that field. Then I spoke about in quite some depth about the work that we are doing here. And I'm very interested in soft robotics and the application of that into to surgery. So different examples of soft robotics are out there. but we were trying to be, very radical and move away from anything that is rigid and develop this soft approach. And you remember these videos, I suppose. So really using silicon rubber, soft materials to create now robotic structures that could be controlled then in all kinds of ways. And obviously, then moving away from these earlier prototypes, we were keen to develop systems that are more suitable for minimally invasive surgery. Miniaturization is a big issue still, but we managed to create something that was 14.7 millimeter in diameter and could be used, theoretically, is ready to be inserted into a human. The dimensions are okay, sensor, camera integrated to feedback information from the inside of the environment. And we had also a study on a human. It was a cadaver study where we were able to put in our device, which you can see here, the soft robotic device, 2 segments and a camera at the tip to observe what's happening inside the human. We also looked at another approach, so not only the silicon rubber approach, but also at systems made from fabric. And these can be inflated, so they can be inflated to be deployed. And here are some examples. You can refresh your memory by looking at the video. I just wanted to show that we were able to create some kind of endoscopic devices, so flexible, inflatable structures that could fit through very narrow openings and then could be moved around inside the human body or a phantom of a human body to observe what's happening during an operation. Very quickly also the eversion robot, so a robotic device that can extend forward. And I can see applications in colonoscopy, for example. It's something I'm working on. And we applied this also to other areas which are outside the medical field. But there was also one approach we have investigated where we were considering this eversion principle for a robotic device that could, penetrate into a abdominal cavity, for example, and then be used as an overtube to bring in other instruments into that remote area. And yeah, here is the colonoscopic kind of approach. So a eversion robot moving forward in a tunnel like a colon, and that could be used then to bring sensors or tools to the remote areas inside the colon. Yep, and of course, one has to be critical there as well. Soft robotics does not necessarily have all the solutions to all problems. Maybe for you to look at and also keep in mind on that. So I think I came to that point, and so I want to just again, but be quick. So that was already mentioned by other speakers. So the interest of now creating devices that can be introduced into the human body through natural openings like the mouth, for example, and then to carry out operations either in that area, in that lumen that we are confronted with, so for example in the stomach, or even to go through the wall of the stomach and then transluminally go into the abdominal area and carry out the operation. And a great advantage, there would be no scar on the outside of the body because you're going through the mouth in this particular case, and carry out the operation. But of course, very challenging and not very widely spread. Because of the challenges, you need to bring your robotic device. So here's a transvaginal approach, for example, being shown. Bring your robotic device in that remote area, create a stable platform, also integrate sensors to then actually be able to to carry out the operation. So, so just to have a stable platform in this remote area is a big problem. So I don't know, maybe it's too much talking there. Okay, maybe, yep, I'll leave that to you to look at. Okay, maybe here we can look at that. So that is the Anubis scope, and that is brought in either through an insertion or through a natural opening, and then used to carry out an operation in this remote location. Good. I move forward. I leave that to you to look at, but that is the main idea, to have now these tools going through natural openings of the body. And some attempts have been also made to actually robotize the Anubis, which is usually the Anubis scope, which is usually a manually operated system. I'll skip that now. I leave that to you to look at if you want. Now, perception, I will just go very quickly over it, not going in too much detail. So there is we have seen a lot of work using cameras, small size cameras, endoscopic cameras, laparoscopic cameras. So that is an important sensor in minimally invasive surgery. Other sensors are being developed. So we have been looking into developing tactile and force sensors, so we can measure the interaction with the tool that is being inserted and the environment. And again, I leave that to you to look at. I would like to so we were interested in, it's a bit too long maybe, so interested in creating devices that could be used by the surgeons to introduce them through a trocar port into the abdominal cavity, and then to interact with the tissue. So effectively simulating palpation. Palpation is possible in open surgery, where the surgeons, go into the body with their own hands. Doing open surgery, that is possible, but it's not possible if you have only a very small opening. But so now to give the surgeon some feel of the tissue, we developed these devices that could be rolled over the tissue and allowed the measurement of forces and stiffness. So we measure the stiffness of the tissue and relate that back to the surgeon, and they can then, that's the idea, understand where we made different devices there, maybe, okay. Anyway, can identify, distinguish between healthy tissue and a tumor in the tissue, and that could guide them then when they carry out the operation. So these images are now here to show you that we considerably reduce the size of these sensors, and I would like to come to this one here. Here we were able to create a 3.2 millimeter diameter system sensor that could be integrated in a heart catheter, and then be used to actually measure the interaction forces between the catheter and the heart wall. And that was a 3-axis force sensor, so we could measure forces in the Z direction and also in X and Y direction. And this is very useful when you carry out procedures in the heart, for example, to treat arrhythmias. Moving forward from that, we were also now able to integrate these sensors into soft structures. So soft sensors being integrated. Do I have another? Yeah, I have this one here. Integrated into a soft structure here, for example, to measure the bending of a system, of a soft robotic structure. As you can see, the information from our bending sensor integrated here is shown here, and shows how this robot finger is bending in stages. Good. Also an overview of the perception aspect, again for you to have another look at it, to see what the challenges are. Especially if we then also try to create softer and softer robotic structures, what kind of sensors can we integrate there? how difficult is it to actually get meaningful information from these sensors that we can then translate into, for example, forces or tactile information being measured. Yeah, so autonomy, I will also very quickly go over that. Please have a look at that as well. That was already mentioned by a number of colleagues, by Elena today, but also Pietro Baldastri spoke quite a bit about levels of autonomy in minimally invasive surgery. And that is, autonomy is not a new thing, and there have been already attempts in the past, so here in 1978, to define levels of autonomy. And yeah, one tries to, you know, kind of get a description of this spectrum. And on the one side, you know, number one, there's no assistance, so it's a completely manual thing that the human is doing. And on the other side, yeah, very high, in this case, level 10, we have the human has nothing to do with it anymore. The robot or the computer system is taking complete control. Yeah? And that's the same also with driving a car. And Elena, I think, made this point very nicely today. So on the one hand, we look at standard cars of today, and you have to have your, I mean, it doesn't work the way it's intended if you take your hands off the steering wheel, and you have to put your feet on the pedals. You know, you have to accelerate and to brake as needed. You are in full control, so completely manual, no automation. And now, of course, Tesla is trying to move away from that and create systems that, you know, are kind of autonomous, can do it automatically, but yeah, otherwise needs our interaction. And we are moving in that direction, but I think we are not quite there yet. And the same applies, so self-drive cars is now shown here as well. Same applies also to surgery, and there's a lot of talk about, you know, how we can move from this very low level to level 5. Some very critical people say even those robots that we are using at the moment are still at level 0. Yeah, even though we have a robot there, so-called robot, the Da Vinci robot, for example, but at the end of the day, it's a tele-operated system. So you need a person there that who is controlling, you know, the device. Otherwise, it wouldn't work. So they need to get the camera images back from the laparoscopic camera, interpret that, make a decision on where they want to go with the tool to carry out the needed cuts and suturing. That's what the very critical people say. There are some elements of support built into the Da Vinci system. So, for example, it has a tremor reduction, so that the tremor is reduced when you use this device, because everyone has a certain tremor, and if you try to do very, you know, minute things and operate on very delicate small items, then you have a natural tremor there that makes that very difficult. So that the Da Vinci system overcomes that issue with a tremor reduction, and also they have the reversal of the movements. I spoke, I think, already about that. When you do laparoscopic surgery, you go through a trocar port that gives you a pivot point. And then if you now want to operate those points, have only the handles on the other side, and you have to move them in the opposite direction to achieve then the desired motion. Yeah? So you have here on the one side, you have your base, and if you now constricted by your point where the trocar port is, then obviously, you know, you move this in one direction, your tip will move in the other direction. So if you want to do suturing, you have to learn to kind of reverse your thinking there to achieve, you know, suturing and making a knot. Maybe you know about these bicycles that you can maybe see on a fun fair where some clever guy has changed the steering. So it is kind of going in the opposite direction. Have you tried those? You've never seen them? No. It's totally crazy. You get on there and you think you can do it, but you turn it to the left, the steering wheel, you know, but the handlebar, but the wheel goes the other way. So you have to try to go in the opposite direction. It's doable, but it takes time to learn. So that's the same problem you have also when you do laparoscopic surgery. Anyway, so levels of autonomy, and I suppose what will happen more and more is that certain simple procedures, maybe suturing along a certain line, will be automated, or guidance will be given to the surgeon. So the robot arm cannot go into forbidden areas to damage any tissue. And that will continue to develop, and possibly one day we have also full automation, but we are still very far away from that, I think. Yeah. Okay. Yeah. So here we have the challenges of autonomy summarized. And that brings me to the end of that presentation.